Well, we're going to have a look at the next of our spectroscopic techniques, and this one's called infrared spectroscopy, and it's quite different from the other four that we've looked at so far because the energy that we are using for IR is of a lower energy level than the ones we used for the previous techniques. So let's just do a bit of a recap on what we've discovered so far. First of all, with the flame colours and the atomic emission spectroscopy, I've drawn a little diagram there to indicate to you that what's happening there when that light is emitted, that's that little wriggly purple thing coming out of the right hand side, that occurs because an electron is descending from a higher orbital to a lower orbital level and is giving off that characteristic light characteristic of the group 1 and 2 metals to which it applies. Okay, so you've got an electron jumping down, descending from a higher to a lower orbital energy state. That's what's going on in those two techniques. On the other hand, with atomic absorption spectroscopy and UV vis, they involve the absorption of energy and the jumping up from an electron to a higher energy orbital state in the process. Okay, so they're different from the first two. They're absorption, whereas the first two are emission. Okay, now this one here, the one we're doing today, the infrared spectroscopy, it involves a lower energy electromagnetic radiation, and this energy does not affect electron orbitals at all. It just isn't a high enough grade of energy, if you like, to do that. So what it does do, it affects the bonds between atoms. The bonds between atoms. It affects the stretching, the vibrating, the rocking of those bonds. These bonds are not static bonds. They're moving all the time. They're dynamic bonds. And when you basically input enough of the right energy, the right frequency of energy, which is resonant with the particular bonds that you are exposing, energy will be absorbed. And that's what we're looking for, okay? That's what we're looking for in this technique. And it's used to identify functional groups such as the OH group, the CH group, the C double bond O group. That's what we're looking to identify. It does have a qualitative and a quantitative side to the analysis, IR does, but for our purposes in our course we're using exclusively really qualitative analysis. I haven't seen an exam question using quantitative at all, and I doubt whether you will ever get one. Okay, let's move on. So, as I've said previously, infrared radiation is lower in energy than the other techniques that we've used, and it has a longer wavelength than visible and ultraviolet light. Therefore, the energy used from infrared radiation is not enough to promote electrons to a higher energy level, but it is enough to cause vibrational changes to the bonds in molecules. Okay, so infrared spectroscopy therefore exploits the fact that molecules are flexible structures that bend and stretch. That's what it's exploiting. Okay, so a molecule will absorb a discrete quantum of energy to move from one vibrational energy level to the next. That's what we're doing. Now, the amount of energy required is provided by the radiation in the infrared spectrum. That's what we're studying now. Down at the bottom of this screen you can see all kinds of stretching and vibrating going on. That's what's happening there. This one here, we've got this middle atom is basically moving laterally towards the both end ones, and you've got all sorts of crazy things going on here. There's a real dance act going on down there with that's a kind of like a wagging. I forget all the technical terms they give them, but it's really funny. If you look up Wikipedia and search for infrared spectroscopy and then dial down a little bit, you'll be amused to see all this little, there's an actual, I call it the disco dancing. You've got all these little bonds wagging, stretching, jigging, absolutely going crazy, having it. It's really party time down there at the atomic level. So yeah, it's pretty amazing. So let's proceed. Right, now, the energy needed to excite the molecule to a higher vibrational energy level is dependent upon two things. The stretch of the bond. Now, I'm going to talk about this in another screen, using an analogy of springs, coil springs. But suffice it to say that a single bond absorbs a lower energy infrared radiation than a what I call a stiffer bond, such as a double or a triple bond. Okay. Now I'll explain why that is when I use a spring analogy, a coil spring analogy, in a later screen, and you'll see what I'm talking about. So it depends on the strength of the bond, that is the energy needed. The energy needed depends on the strength of the bond, and also it depends on the mass of the atom bonded to the carbon. Now, okay, the higher the mass, the lower the energy absorbed. Again, look, you'll understand this when I explain it with my spring analogy, and that's coming up. Okay, so we'll deal with that later. Alright, these characteristics of the infrared spectrum make it a powerful tool for identifying the bonds and the functional groups in the molecules. Okay, now the IR spectroscopy frequency. Now this is a really weird one. It's basically measured, the frequency is measured as what's called the wave number, and we're looking at the wave number is basically 1 over the wavelength. That's what the wave number is. And if you, knowing that the speed of a wave is equal to its frequency times its wavelength, if you transpose that formula down here, you will get that 1 over the wavelength is equal to the frequency over the speed. The speed is the speed of light for all electromagnetic radiation, so that's a constant. So what I'm trying to say is that the wave number, or the reciprocal of the wavelength, same thing, is a direct measure of frequency. Now, don't ask me why they measure it like that, I don't know. But basically that's what it is. And the wave number, being the reciprocal of the wavelength, is measured as centimetres to the minus 1, or 1 over centimetres. Okay? Now, so that is our unit of frequency, wave number, measured in centimetres to the minus 1. Now, at the bottom of this screen, you can just get there's a few little things described there. You can see that as the bonds get stiffer and stronger, you can see that the bond energy, in other words, I'll talk about it in the next screen, I think it is. The frequency of absorption is higher, of IR radiation is higher. Okay, and there it is. Yeah, the infrared absorption is higher. Don't worry about that. That's just increasing energy and increasing frequency of IR energy absorbed. Now, what's over here? Oh yeah, look, this is just describing, see there, you've got a hydrogen there, you've got a carbon there hooked up to that left-hand carbon, you've got an oxygen here, a chlorine there, and a bromine there. Now, as we're getting down that table, those right-hand atoms are all getting heavier and heavier and heavier, and as they get heavier, you get a decreasing energy absorption. Now, if that's all confusing you, don't worry about it. I think you'll understand it when I talk about the spring analogy on the next screen. Now, the other thing to notice at the bottom of this thing here is that these frequencies are typical values only. Typical values only. The absorption actually occurs over a band of frequencies. A band of frequencies, because every bond in a molecule interacts. So the whole thing is basically all interrelated and complicated. So you have to just think about it as a band of frequencies over which you can expect absorption of certain functional groups to absorb their energy, absorbing their energy to occur. Okay. All right. Now, what we're looking at here is some instrumentation. Now, this diagram here is extremely complicated and it's hard to work out. I don't think it's particularly well drawn, but the essence of it is that you've got a little chopping unit here, a chopping unit in there, basically, and that chopping unit, where do I just rub that out again because it's making it, yeah. Now, that chopping unit is allowing the computer, the infrared detector, and the computer, wait a minute, there you go, the infrared detector and the computer to continuously compare the sample to the reference cell. The chopper basically just means that you're continuously swapping from one signal to the other, 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 so that the detector is going sample signal, reference signal, I can't say that too quick, sample signal, reference signal, sample signal, reference signal, and so on and so on and so on. So that's how you basically measure what the actual absorption is of the sample, okay? Now, I think that's what I just said, isn't it? The infrared radiation from the source is split into two beams and passed separately through the sample cell and the reference cell. Yes. The difference now, this is the other weird thing I want to explain to you. In IR, we don't measure absorbance, we measure transmittance. So that when something gets absorbed, here's your wave number, like that. Actually, that's not right. They go the other. They go the other way. These things. They measure them from a left-hand column, and they go like this. They go. I mean, from the right-hand side, they go like that. So that then, when you're measuring, you get all these peaks. Instead of, they're reverse peaks. They're troughs, and these troughs are actually your transmittance. And the transmittance, when you get a trough, that basically corresponds to a peak of absorbance. So these things are peaks of absorbance, which are troughs in transmittance. All I want you to know from all that is that when you get a low point, that means you've got absorbance going on at that low point. Okay? That's all you've got to understand. Don't worry about all this transmittance rubbish, but you will see the word transmittance on the vertical axis. And that is corresponding to the kind of the reverse action of absorption. Okay, where was I? The difference in transmittance or transmitted radiation between the sample and the reference cell is due to the absorption, okay, of certain frequencies by the molecules in the sample. Okay, last but not least, these absorptions result in changes of the vibrational energy in the molecule under examination. Okay, are you still with me? Good. Now, here we go. The interpretation of an infrared spectrum. Okay, we're going to look at qualitative analysis, because that's by far the more important of the two. Quantitative I've never ever seen a question on in an exam. So, let's go. IR spectroscopy is most important for identifying functional groups in a molecule, as I was saying. The energy of the radiation absorbed and released depends on the kinds of bonds. This is where my spring analogy is going to be coming, and I'm going to explain it a little bit to you. The kinds of bonds, double or single or double or triple bonds, and we're talking about these bonds acting like springs. This is like a loose spring here, this is like a tighter spring, and this is like a really, really strong spring. And if you pull something on the end of that spring, it's going to be slowly vibrating backwards, upwards and downwards. This one here is going to be basically going faster, and this one here, it's going to go boing, 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 because it's going to like it's a really strong spring. Okay, and also not only the kinds of bonds that to work out the frequency of the radiation absorbed, it's not only the kinds of bonds, it's also the environment or the other bonds in the molecule. Now, let me just start to explain what I'm talking about here in terms of this spring thing. Now, there's a spring, and this spring, the frequency of the spring is basically analogous to the frequency of the IR energy absorbed. Okay, if you pull on that weight, and that weight represents an atom, at the end of a bond, okay? And the spring itself represents the strength of the bond, single or double or triple. Now, if you pull on that ball representing an atom, the whole thing's going to vibrate upwards and downwards. And the frequency of the vibrating upwards and downwards is analogous to the frequency of the energy, the IR energy absorbed, okay? Now, if you have a heavier ball on the end, you think about that and you pull on it, it's going to vibrate slower. Like a bowling ball is going to vibrate a lot slower than a golf ball, isn't it? Well, that's what I'm sort of saying, okay? So you can use that as an analogy for working out the frequency of the IR energy absorbed, okay? The other thing, yeah, heavy atoms slower, frequency, yeah. Now, the other thing is stronger bonds, they basically the stronger the bond, the stiffer the spring, if you like, and therefore the faster the frequency. So that also passes the test for working out the trends in IR energy frequencies absorbed. Okay, so if you had a triple bond, carbon to carbon situation, then you would be expecting the IR energy absorbed, the right resonant IR frequency absorbed, to be of a much higher frequency than if you just had a single carbon to carbon bond representing a much looser spring which vibrates slower. I hope I explained that reasonably okay for you. Okay, and it helped me a lot to understand the trends, you know, but it's just trends. You don't have to get too hung up about it. They don't ask too many questions about that anyway in the exams. Now, all this stuff over here gives you a very, very complicated looking diagram, but you just got to remember these troughs at these particular wave numbers along here. These troughs are representing energy absorbed by various functional groups, okay? But when you get below about 1,000 wave numbers, forget it. You're not looking at functional groups anymore. You're actually looking at the flexure and the vibrating of the backbone of the molecule itself, not of the functional groups on the molecule. And that we don't worry about that part of it. That's called the fingerprint region, which is unique to the structure, the backbone or the chassis of the molecule. Okay? Okay, now, no two molecular compounds are identical in the bonds and the bonding environment, and therefore IR can give us a characteristic fingerprint for each compound. Some peaks are narrow, yeah, some peaks are narrow. For example, the C double bond O is a very, very, like a stalactite in a cave. It's very, very jagged and it hangs down, and it isn't a broad one at all. Other peaks are broad. Typically the OH one is very, very broad, and that occurs at a characteristic frequency of around 3000. I only remember 3 of them, by the way, so I'll tell you the 3 that I remember. The absorption bands in the spectrum above 1,000 wave numbers are used to identify functional groups. Less than 1,000 wave numbers, as I said, is called the fingerprint region, which has got nothing to do with functional groups. It's only to do with the actual backbone or the chassis vibrating and flexing of the actual whole molecule itself. We don't even consider the fingerprint region in any of the work that we do in chemistry. We just basically confine ourselves to the functional group part of it, which is above 1,000 wave numbers roughly. Okay, now by the way, your data book that you use for the exam will have typical wave numbers for various functional groups, and this is something akin to what you might see in your data book. Okay, now what is this example asking us? It says that the structural formula and infrared spectrum of ethanoic acid are shown in a figure over the page. The bond types present in ethanoic acid can be identified from the structural formula. Okay, use table 7.8 above, that's this table up here, to identify the bond types corresponding to peaks A, B and C. And it is useful to summarise this in a table. Alright, well look, we'll just have a look and see what we've got. Goodness gracious, it looks very complicated. Well, I'll tell you the ones that I always remember. Now, ethanoic acid, what's that? Let's just draw it out. You got CH3, you got C, that one, and you got an OH. So if I was you, I'd be looking for C double bond O, which is always easy to, these are the three that I remember, by the way. First of all, C double bond O, which is always this one here, around 1500 wave numbers, and it's really sharp, really sharp. It's always easy to pick, C double bond O. Now the OH one is always a big broad one, around about 3000 wave numbers. That's definitely the OH. And the CH bond, the CH one is usually just to the right hand side of the OH, and it's just a little bit of a pimple, okay, compared to the depth of the OH one. It doesn't go as deep. So they're the only three that I ever remember, by the way, guys. So I wouldn't get too hung up about it, and you will see some of these things in your data book. Now, if they ask you an IR question, it'll usually be in the context of a few different clues that they give you as to the structure of a molecule. They'll give you some IR spectrum, and they'll also give you some NMR spectrum as well, and they'll probably also give you some data which you can work out the empirical formula of a compound with as well. So it'll usually be a multi-stage question. Okay, so don't worry about that. You'll be able to do it just fine when you have a bit of practice. Now, what did they say the solution was? Peak A is a broad peak, maximum in the L. That's the OH one, I can tell you that. Oh, look, I got it right. Very good. And the peak at 2990, that's going to be the CH. Yes, I got that one right too. Jolly good show. And the peak, did they do this? Yeah, they did the C double bond O as well. That's the one, that's this one, the big, jagged, deep one, sharp one. Okay, that was pretty easy. This stuff isn't all that complicated, so don't be put off by all the weird looking shapes. You'll get used to it, and it's not that difficult. They can't ask you anything too hard anyway. I mean, you're not a university professor, you're just a year 12 chemistry student, so don't worry, don't get stressed, it's okay. Yeah, the peaks below 1000 wave numbers are more difficult to interpret. That's the fingerprint region, isn't it? As we've been discussing. Okay, now this little screen here talks about quantitative analysis, which I've never even done a question in quantitative analysis, so I wouldn't get too worried about it. But they, just for the sake of completion, we'll cover what they talk about. They say here that what you do is you pick a strong, sharp peak in the spectrum, similar to what we did with UV vis, and then picking that wavelength using various concentrations of the substance, you will basically make up a calibration curve, just the same as we did with the other techniques, and you'll get probably absorbance or transmittance, I'm not sure which, and you'll get concentration at the particular wavelength that you chose, and then your sample. When you get your sample, these are known concentrations, of course. When you get your sample, you get the absorbance and you read it off, and Bob's your uncle, you've got the concentration. So that's how they do it, but I have never even seen a question on quantitative analysis using IR, as I say. Now, what do they say here? Yes, that's what we just said. The concentration of the sample is found by comparison with the calibration curve, yes, but look at this. Unfortunately, the calibrations are often significantly curved rather than linear, so that's a little bit tricky, isn't it? So probably that's why they don't ask you any questions on the quantitative side of IR. Okay, we're there. Let's just see what we've got here. We're saying that infrared spectroscopy can be used to identify molecular structures and verify the identity of unknown compounds. The covalent bonds between atoms vibrate due to stretching and bending motions. These cause a change in the dipole moment. Oh yeah, the dipole moment. I better talk about that. Molecules have discrete vibrational energy levels. The absorption of infrared radiation causes molecules to move to higher vibrational energy levels. Yes, we know that. and each covalent bond absorbs infrared radiation over a characteristic range of frequencies called wave numbers, enabling the covalent bond and the structure of the compound to be identified. Okay, now each compound has a unique absorbance pattern. Yes, we know that in the fingerprint region of the infrared spectrum, and this can be used to identify the compound. Yes, we know that, but I've never seen an exam question using the fingerprint region. Now, only to do with functional groups. Now, the dipole moment stuff, what you've got to just tuck away in your knowledge bank is that if you have a molecule, a monatomic molecule such as nitrogen, something like that, where you had N2, these things, because there's no difference in the electronegativity of the two components of that molecule, they're the same thing, then there's no dipole activity. In other words, there's no delta plus or delta minus ends to this molecule. They're basically homogeneous, okay? And therefore, in that situation, they do not work with IR at all. You'll never get them to work. They don't absorb infrared energy in the way that we use it for spectroscopic analysis, okay? So you have to have a dipole moment. You have to have something different, such as CH, something like that, okay? There's a dipole associated with that. Basically, the carbon, although it's not very electronegative, it'll be a little bit more electronegative than the hydrogen, but not much. But nevertheless, there is a dipole, and that's the kind of thing you need for IR to work in terms of these functional group behaviours and the resonant frequencies that they will absorb. Okay, my goodness. I hope you enjoyed all that. Don't get too hung up about it. It's pretty easy in practice, and you'll master it just fine. See you next time.